Quantumology. Today I'm looking at electrons and what they are, what they mean to us, etc. So first of all, they are elementary fermions. Fermions are particles that relate to the material world, the matter that we are familiar with. So that's essentially why they are categorized as fermions. They're also categorized as leptons. So if you have a look at the standard model of physics, you will find their categories there and explanations thereof. So do have a look at that. Okay, so what we've got here is the familiar electron that is negatively charged. It exists in our universe as a negatively charged particle. Its opposite number is the positron, so that's its antiparticle, and the positron is positively charged. We looked into this a little bit while ago. J.J. Thomson was playing around with cathode rays, and in conjunction with Townsend and Wilson, a couple of other physicists, he found that cathode rays were unique. The particles that they emitted had some kind of weird property that made them unique to any of the other particles that were known about at the time. And as these explorations went further, they then became known as electrons. That was the term that was later adopted for their use. So very early on, we had a physicist called Rutherford who came up with this model here. And he had the electron orbiting the nucleus of the atom. It was then later found that, in fact, that wasn't quite right, because electrons don't orbit the nucleus of the atom as such, in the same way that we would consider planets, for instance, to be orbiting the sun. It didn't work quite that way. So then there was another model came up, Bohr. He more accurately determined that electrons existed in shells around the nucleus of the atom. Now, as time went on, it was becoming more obvious that electrons are very strange particles. They're very fuzzy, they vibrate, they exist in a sort of frequency level, and there was even debate as to whether there was just one electron in the whole universe that zipped around and existed everywhere, but that's another story. So there is a one electron theory if you want to look into that more deeply. Okay, so we've got this shell structure here, and the electrons are dropping in energy level and rising in energy level all the time. They have this kind of flow, this flux of energy within the atomic structure. So this outer shell represents the place where an electron will have most energy. It's most energetic the further away from the nucleus it is. When it gets very close to the nucleus, it's at ground state, which is the lowest energy form that it can take. Now it's quite interesting how it moves between these states, because this is all to do with its relationship with photons. Essentially, here's the average line, say, of the electron's energy level. This is the average line here. If it wants to go up an energy level, it absorbs a photon. And if it's going to drop a level towards ground state, then it loses a photon. So you've got this movement happening within the atomic structure all the time, of electrons going up and down according to whether they're taking on a photon or losing a photon. One aspect of how electrons exist and what they do. There's another really important thing that electrons can do too, along with other quantum particles which do the same thing. Now this is a wave, represents a wave of whatever field or material a quantum particle is moving through. And what you've got here is a probability well. That's what this represents. So there's your electron sitting down there in the bottom of this probability well. It takes quite a lot of energy for it to move up and over the hill, if you like, of the waveform. So it may decide, for whatever reason, that moving up and over and into the next probability well over the hill is far too much effort. And it really can't be bothered with all that. So it goes straight through into the next probability well using what's known as quantum tunneling. Quantum tunneling is another wonderful phenomena that is well worth looking up in your exploration of quantum principles and particle physics. So I'll just write that in there because that's quite important. Quantum tunneling, that's what that's doing. So then, amongst all these questions and things, there are various other phenomena going on. Let's go back to this for a minute, this electron-positron relationship. So you've got an electron negatively charged, you've got the positron which is positively charged, and the positron doesn't belong in our universe. When it comes into our universe from wherever it comes from, it will meet an electron and they will immediately annihilate. So this is the central point here. And that annihilation between the electron and the positron produces a photon, and that photon then decays into a quark and an antiquark. And the antiquark also produces a gluon. Now where does that gluon go? What happens to it? Since it's produced by the antiquark, does it come into this dimension, into our reality, or does it go somewhere else? Question worth asking. Okay, the most familiar format that we would think about electrons being in is, of course, electricity, as the name suggests. So here we've got a representation of an electrical current. Now what happens with this? How does electricity flow? Well, the material, usually metal and wires, the atoms of that material are fixed. They stay in a fixed place. But the electrons, they get kicked from one atom to the next. So they move by getting kicked from atom to atom to atom. That's how electricity flows. All this happens faster than we can possibly imagine. So when you switch on your light switch and the light bulb comes on instantaneously, that's why. Because this process occurs, relatively speaking, in terms of relativity, much faster than we can possibly comprehend. And what does that mean for us? Well, we're made of atoms, so obviously we've got a lot of electrons buzzing around in there. They're going up energy levels, they're dropping energy levels. How does that relate to our energy levels? Do our personal energy levels, when we're full of energy, do we have more of the higher taking on photons thing going on? When we're low in energy, do we have more release and losing of photons going on? What's the relationship between electrons and photons, electromagnetism, light, etc.? These are all questions that are well worth asking. So is there a deeper relationship with photons than we know about? Okay, well, that essentially is the end of it today, and I hope you've enjoyed this. If you want to know more and you want to get involved with the live discussions, then come along to Quantumology and find out what we're doing. I hope to see you again soon. Thanks a lot. Bye.